Hi, I'm Srđan Đorđević of Cadence Design Systems. Welcome to Sigrity Tech Tips. Today, we bring you another installment of how to build and verify your multi-gigabit serial link to meet industry compliance standards. Our video today will show you how modules designed for automotive applications can be verified for compliance of the automotive Ethernet standard before design prototypes are brought to the lab. Utilizing the Sigrity serial link analysis methodology and our automotive Ethernet compliance kit, confidence that your design is compliant with the standard can be achieved through simulation. No longer will the first indication be when a physical test bench is created in the lab and test equipment is used to measure the PAM3 signals after they pass through meters of twisted pair automotive Ethernet cable. Instead, compliance issues are caught before building physical prototypes, and when the prototype does reach the lab, measurement is performed to verify instead of debug design. With the complete automotive Ethernet solution, you will be able to pass industry compliance tests the first time. Your product will get to market on time, your team will look good, and your module just might generate significant profits for your company. In today's video, you will see us utilize the Allegro Sigrity SI base and system serial link analysis option. To learn more about these products, visit us at www.cadence.com. Now, I will turn it over to my colleague Ken Willis.
Thanks, Srđan. This is Ken Willis from Cadence Design Systems. This demonstration will be for the 100 base T1 compliance kit in System SI serial link analysis. Electronic content has increased dramatically in cars over the last 10 years. High-speed connections are now required between things like sensors, processors, and cameras, especially for applications like ADAS, which is Advanced Driver Assistance Systems. Some of the newer models of vehicles include over 100 processors in them to handle all this communication. The interconnect between all these different processors is done with an automotive Ethernet standard defined by IEEE as the 100 base T1 specification. This diagram gives an example of what an automotive Ethernet channel may look like. The SerDes PHY is located on an ECU or an electronic control unit board and drives through a package, through the board, to an MDI connector, where MDI stands for Medium Dependent Interface. The signals then travel over some length of unshielded twisted pair cable, and you may put multiple cables together with inline connectors. The signals are then received at the other ECU board, where line conditioning or equalization may be applied to clean up the signals. As you can see in the picture, PAM3 signaling is used over these links to help reduce bandwidth and reduce EMI. Now let's take a look at the 100 base T1 compliance kit that's built into System SI. This compliance kit comes with two templates. One is for looking at the compliance criteria for the transmitter, and one for the receiver. This one is for the transmitter. If we zoom in, we can take a closer look. The topology starts with the transmitter, goes through the package, the PCB, and the MDI connector. If we double-click on the MDI connector block, we can view its S parameters. Here you can see the return loss curves. We can also show the insertion loss. So this has an example S parameter in it for MDI connector, but the user is expected to replace this with their own specific model for the connector that they're using. If we scroll through the topology, you can see that there's a number of cable and inline connector models here, but they're ghosted out. And what that means in System SI is that they've been designated to be a short. So they're just shorted out. So they're not really included in the simulation at this point. So you basically have the topology, you've got the board through the MDI connector driving to the receiver. Now we can look at the compliance checks associated with the transmitter. These include the droop test, the jitter test, the power spectral density test, and also the transmitter peak differential output test. So we'll turn on all the compliance checks for the transmitter and kick off the analysis. When the analysis is completed, the sign-off report will appear. This shows us links to the spec, a diagram of the general topology, and then a summary of all the results from the compliance checks that we decided to run. The first test is for transmit droop. The maximum allowable droop is 45%, and you can see in this case we passed because we're less than that at around 28%. If you click in the table, we'll bring up the plot. In this test, we have to transmit a long string of +1 and -1 symbols in the PAM3 scheme, each for longer than 500 nanoseconds. After that, we have to measure to see that the maximum droop is no greater than 45% of the initial value of the signal. With the transmit jitter test, we capture the waveforms at the MDI connector. We then post-process and compute the RMS jitter that we see there. The spec limit is 50 picoseconds RMS, and we're well below that at about 35. So this compliance check passes. The next check is for power spectral density of the transmitter. The report indicates that we failed this one, so let's go take a look at the plot. This test essentially applies a spectrum analyzer to the simulated waveform. You can see that we intrude into the mask area at the lower frequency ranges, and we may need some transmitter adjustments to pass. The other transmitter compliance check that we have here is for peak differential output voltage. The spec limit is given at 2.2 volts, and you can see that our actual value is just slightly under 2 volts, so we pass. Zooming in on the waveform plot will give you a closer look. Next, we'll look at the template for the cabling system and the receiver compliance checks. This template is very similar to the transmitter template we looked at. In contrast, though, you can see that the cable models and the inline connectors are not shorted out, and they are all in place. This template contains 5 cable models, giving you an equivalent length of 15 meters. The cable models and connector models can easily be turned on or off to adjust the length, or you can replace with your own models. The kit also comes with a PAM3 aware receiver AMI model, which contains multiple modules. One is the AGC, or automatic gain control module, the continuous time linear equalizer module, and the DFE module for decision feedback equalization. Any of these modules can be turned on or off in the overall AMI model. Next, we can look at the compliance checks for the cabling system and for the receiver. For the cabling system, these checks consist of characteristic impedance, insertion loss, return loss, and mode conversion loss. For the receiver, we will check the eye height and the eye width at a bit error rate of 1e to the -10. Users can enter in the requirements for their own receiver. In this case, we'll enter 50 millivolts for eye height and 0.5 UI for eye width. We'll turn on these compliance checks and kick off the analysis. When the compliance report appears, it again shows us links to the specification, a diagram of the overall topology, and a summary of the results from the various compliance checks that were run. For the cabling system or the interconnect, we can see we've passed some of the tests and we failed some of the tests, so we can go look at the results. The characteristic impedance plot essentially gives us a TDR measurement. Looking at the plot, you can see a small spike where the impedance goes just outside of the compliant region, which creates the fail condition in the compliance report. If we toggle from here over to the insertion loss plot, we can see that this one passes as the results stay outside of the mask region. We can also toggle over to the return loss plot, which gave us a failure in the compliance report. We can zoom in on the plot to get a closer look. Since the return loss result intrudes on the mask region, this indicates that there's a reflection problem we'll need to address somewhere in the topology. The next result is for mode conversion loss, which checks the common mode to differential mode conversion in the interconnect channel. Here you can see that the result does not intrude into the mask region, so this compliance check passes. Next, we'll look at the eye height and the eye width compliance checks at the receiver. Both of these checks pass at the bit error rate of 1e to the -10. The requirement we entered for eye height was 50 millivolts, and you can see here the simulation result is just slightly over 50 millivolts, giving us a passing grade. Looking at the plot shows you just how close that is, so there's actually not much margin in this particular check, even though it passed. Looking at the bathtub plot for the eye width, you can see that we have significantly more margin here. The red arrow indicates the requirement, and the bathtub curves show you the actual value from the analysis. We can also simulate the channel directly, and of course you can substitute all of your own models in for any of the blocks, or add or delete any of the blocks between the receiver and the transmitter. During the channel simulation, there'll be real-time plots from the receiver's AMI model showing you how the DFE coefficients are adapting and also how the CTLE is adapting. When the channel simulation completes, we can go in and look at the different eye contours for the PAM3 signals and also look at the various bathtub curves. These are plotted for the composite eye as well as the individual eyes that make up the overall PAM3 eye diagram. You can also review the eye density plots in both 2D or 3D views. So, in summary, the 100 base T1 compliance kit has been incorporated into System SI for automotive Ethernet applications. Templates are provided for transmitter, cabling system, and receiver compliance checks. Users can replace those example models in the templates with their own and check compliance to the 100 base T1 IEEE standard. PAM3 simulation and PAM3 aware equalization models are included. That concludes the demonstration. Thanks for watching.
Thank you for watching another edition of Sigrity Tech Tips. For information on products used in today's video, click on the links below or contact your local Cadence sales representative or Cadence channel partner.